Quantum free electron theory is the topic of discussion in this lecture. In our earlier discussions, classical free electron theory was discussed, wherein we understood that the classical theory was successful in explaining a few properties of electrons in metals. However, it was unable to explain few other properties. The limitations were explained in the earlier classes. Quantum theory was proposed by Sommerfeld in order to overcome the limitations of the classical free electron theory. This particular theory is based on the Pauli's exclusion principle. What is the principle? That is Pauli's exclusion principle. According to this principle, no two free electrons can have the same energy value or the same energy level if they have the same spin. If two electrons are to be accommodated at the same energy level, then it is essential for them to have the opposite spins. That is the Pauli's exclusion principle. And in addition to that, the quantum free electron theory assumes that the electrons will possess the quantized energy values. Let me tell you about the assumptions made by the quantum free electron theory. There are four assumptions importantly. One is that the energy values of the free electrons are quantized. That means for given electrons, a set of allowed energy levels are allowed. Allowed energy levels are available. The second assumption is that distribution of electrons at different energy levels is based on the Pauli's exclusion principle. And the third assumption is that the attraction between the electrons and the positive ions and repulsion between the electrons themselves is negligible. And fourth assumption, the electric potential is constant throughout the metal. That means the free electrons travel within a region of constant electric potential. From these four assumptions, you can understand that two are retained from the classical free electron theory. The first two assumptions are new. I mean, they were proposed by Sommerfeld in his quantum free electron theory. The other two, that is about the attraction between electrons and ions, repulsion between electrons themselves, is ignorable, and the constant electric potential. These two assumptions are simply retained from the classical free electron theory. In order to understand the merits of this quantum free electron theory or the success of the quantum free electron theory, or how this particular theory was successful in overcoming the limitations of the classical free electron theory, it is necessary to understand a few terminologies such as Fermi energy, Fermi velocity, Fermi temperature, effective mass, etc. So now let us go one by one so that we will understand the theory in a right manner and in a simple manner. Let me first define the Fermi energy. Fermi energy is the energy corresponding to highest occupied energy level of electrons at 0 degree absolute temperature. The highest occupied energy level of electrons is known as the Fermi level. Fermi energy at 0 degree Kelvin can be expressed using this relation. Here H is the Planck's constant, m is the mass of electron, n is the number of electrons per unit volume. This relation is establishing a relation between the Fermi energy and the free electron density in a given conductor. By substituting the constant values, that is H is equal to 6.625 into 10 power minus 34 joule second, and M, rest mass of electron, is used here 9.1 into 10 power minus 31 kg. By substituting these constants, it is possible to get this expression as EF naught is equal to 5.85 into 10 power minus 38 into n power 2 by 3. And at a high temperature, the expression is given by EF is equal to EF naught into 1 minus pi square by 12 kT by EF naught power 2. Here EF naught is the Fermi energy at 0 degree absolute temperature. T is the temperature at which this Fermi energy is measured, and K is the Boltzmann constant. This equation suggests that the Fermi energy is not the same at all temperatures, and this decreases with increasing temperature. Let me tell you in brief about the Fermi energy. I can show diagrammatically that if there are two electrons in a given system having the opposite spins, then they can occupy the lowest energy state according to the Pauli's exclusion principle. And if there are two more electrons of opposite spin, then they have to necessarily be accommodated at a higher energy level. So if you think there are 5 electrons, then fifth electron occupies the next higher energy level. In this way, the energy levels can be assumed to be n in number for n number of electrons, and if that system has only 6 electrons as drawn here, this represents the Fermi level. Or if some more electrons are added to the system, free electrons are added to the system, then this Fermi level can rise to even to this level or to this level or to this level. So as per this diagram, you can understand that these are the allowed energy levels. These are the allowed energy states, whereas these are the vacant energy levels. These are vacant energy levels. This is the Fermi level. This is Fermi level. That means this is the highest occupied energy level at 0 degree Kelvin. This is how one can understand the concept of Fermi energy. Fermi and Dirac proposed a statistical theory in order to explain the probability of distribution of electrons in different energy levels using the Pauli's exclusion principle. That statistical rule according to which electron distribution takes place at thermal equilibrium condition in various energy states is called Fermi-Dirac statistics. This is applicable to the system of electrons obeying Pauli's exclusion principle. That is Fermi-Dirac statistics. According to this theory, there is one distribution function which is represented with the symbol f of e. It is also called Fermi factor, it is expressed as 1 divided by e power e minus ef by kt plus 1. Here in this equation, E is the energy corresponding to any energy level. It may be either above the Fermi level as shown in this diagram. This may be corresponding to E, or this may be corresponding to E. So E is the energy level corresponding to any energy level chosen. And EF, as we have already understood, it is the Fermi energy. K is Boltzmann constant and T is the temperature at which this probability of occupation is calculated. One can observe from this equation that the probability of occupation depends on temperature and of course the difference between E and EF. Let us now understand the relation, or let us understand how this probability of occupation varies according to the temperature or according to the difference between E and EF. Let us now look into the relation between the Fermi factor and the temperature. Let us understand how the Fermi factor varies with temperature and of course with the difference between E and EF. Let me consider the first case, case 1. That is, for E smaller than EF at temperature equal to 0 degree Kelvin. Let us consider this case. We have the equation. Let me say it is equation 1. In this equation, if we substitute the values given here, what would be the f of E value? T is equal to 0 means in this equation the denominator of this power of the exponent becomes 0. So that the power of this exponent becomes infinity. I can write here f of E is equal to 1 divided by 1 plus e power infinity. But you have to note here that we are taking that E is smaller than EF. That means we are considering an energy level below the Fermi level. In this case, this would be negative. That means EF is greater than E. Here in this mathematical term, if EF is greater than E, it is negative. So that it is e power minus infinity. This can also be written as 1 plus 1 by e power infinity. So it is 1 divided by 1 plus 1 divided by infinity. 1 by infinity is 0. So 1 plus 0, 1 by 1. So final answer is 1. That indicates, this value also suggests that it is 100%. Probability of occupation of energy levels below the Fermi level is 100%. That means every energy level below the Fermi level, every energy levels below the Fermi level are completely filled by electrons. That is the inference of this part of discussion. And now let us take the second case, case number 2. That means for energy levels above the Fermi level at the same temperature, that is at 0 degree Kelvin. At this temperature, what is the equation? F of E is equal to 1 divided by 1 plus, in this equation, e power infinity. It is plus infinity because E is greater than EF. Now we are considering the energy levels above the Fermi level. These energy levels which are lying above the Fermi level. In that case, This is equal to 1 divided by 1 plus infinity. That is equal to 1 by infinity, which also gives you the value 0. That means at 0 degree absolute temperature, not even a single energy level is occupied by electrons at an energy level above the Fermi level. So all energy levels above the Fermi level, here all energy levels above the Fermi level are vacant. They are not filled by electrons. That's the meaning of this particular case, discussion of this case. Now in the third case, let me take in the third case, assume that E is equal to EF but T greater than 0 degree Kelvin. Okay, if temperature is different from 0 degree absolute but E is equal to EF, what would be the case? You can understand from the equation that if E is equal to EF, numerator is 0. So that we will get E power 0. E power 0 is 1. Therefore, f of E is equal to 1 divided by 1 plus E power 0. Means this is equal to 1 divided by 1 plus 1 equal to half. That means it is 50%. Probability of occupation is 50% in case you consider the Fermi level itself, that is the energy level corresponding to the Fermi energy. So at this level also, at a temperature higher than 0 degree absolute, probability of occupation is 50%. It is not 100%. In case E is greater than EF or E is smaller than EF, what would be the situation? Now let us understand that case. In that case, if E is greater than, let us say it is very high compared to EF in the same equation, that is in the Fermi Factor equation, if E is very much higher than EF but at T different from 0 degree Kelvin. In that case, f of E value, f of E value can be shown to be different from 0.5. That means you can observe that it is almost equal to 0. It is possible to show this. How to understand this? Let me tell you. In this equation, if I say that E is very much greater than EF, if E is very much greater than EF, then here this power becomes positive. And if E is very high compared to EF, I can say that E is infinite. If E is infinite, then the power of the exponent becomes plus infinity. That is E power plus infinity. So f of E is equal to 1 by 1 plus E power infinity. That is when if E is very high compared to EF. So when E is relatively high, then E can be assumed as infinite. In that case, this power gives you infinity and E power infinity is infinity, which gives you 1 by infinity or 0. This means that at higher temperature, at sufficiently high temperature, and if we consider an energy level very far from the Fermi level, that for that energy level will be definitely vacant. That is the meaning of this calculation. If an energy level considered well above the Fermi level at temperature different from 0 degree absolute, then that energy level is definitely vacant. In case E is very small compared to EF, Assume that this is the Fermi energy or Fermi level, and if you are considering an energy level well below the Fermi level, then we say that TF is very considerable as compared to the energy level which we are considering. In that case, EF can be treated as infinity. Here in this equation, you can think that EF is infinity. If that is the case, e power minus infinity will be the answer. That means f of e will be 1 by 1 plus e power minus infinity. If this is the case, what happens? 1 divided by e power minus infinity is 0, because e power minus infinity can be, it was shown here, it is of the similar type. E power minus infinity is 1 by e power infinity, that is 1 by infinity is 0, so we will get 1, that is 100%. We will get 100%. That means even at the temperature different from 0 degree absolute, an energy level well below the Fermi level is definitely filled by the electrons. That is the inference of this calculation. Let me summarize. In this part of discussion, I was talking about the variation of Fermi factor or probability of occupation with temperature. In the first case, I had taken E less than EF at temperature 0 degree Kelvin. So if it is 0, absolutely for any value of E and EF, this is infinity. In case if E is considered to be very high, very small as per this case, if it is very small compared to EF, in that case this infinity is negative. Therefore we will get 100%. And in the second case, if E is very high compared to EF at the same temperature 0 degree absolute, here E is greater than EF, therefore it is positive. T is 0, which makes this positive infinity, therefore e power infinity is giving infinity, resultant value is 0. And in the third case, at higher temperatures, three cases are considered again. That is, if E is equal to EF, f of E is half, that is 50% probability. And if E is greater than EF, we will get 0% probability. That means not even a single energy level is occupied by electrons at an energy level well above the Fermi level. Or if E is very small compared to EF, f of E is 100%. Based on these values, it is possible to draw a graphical diagram to show the variation of probability of occupation. It can be shown in this diagram. One can observe that in this graph we have taken the Fermi factor along y-axis and energy along the x-axis. At temperature is equal to 0 degree Kelvin, when E is smaller than EF, since this point corresponds to EF, for all values of E smaller than EF, the probability of occupation is 100%. Whereas for all energy values higher than EF, the probability of occupation is 0. And at higher temperature, at temperature greater than 0, we could show that 100% probability is there for E very small compared to EF. Whereas if E is very high compared to EF, it is 0. And if E is equal to EF, it is 50%. So mathematical calculations gave these few values which have been plotted here in order to understand how the Fermi factor is varying with the energy as well as the temperature. Let me tell you about the Fermi temperature. Fermi temperature. It is represented with the symbol TF. This is defined as the temperature at which average thermal energy of free electrons become equal to Fermi energy at 0 degree Kelvin. It is the temperature at which average thermal energy of free electrons become equal to Fermi energy at 0 degree Kelvin. The thermal energy of free electrons is approximately kT, Boltzmann constant and absolute temperature. And in terms of the Fermi temperature, you can express it as kTF. Therefore, you can express a relation that EF is equal to kTF. Generally, Fermi energy is of the order of a few electron volt. It is about 2 to 4 electron volt for metals. If we take an average value, that is 3 electron volt here in this calculation, 3 electron volt means it is 3 into 1.6 into 3 into 1.6 into 10 power minus 19 joule. If this is substituted in the place of EF and K, 1.38 into 10 power minus 23. On substituting the values of K and EF, it is possible to obtain the value of TF to be nearly 34,800 degree Kelvin. What does it indicate? This indicates that the temperature of a metal should be of the order of 34,800 degree Kelvin if it has to possess a thermal energy equal to 3 electron volt. But this temperature is too large. It is difficult to achieve this temperature practically, so Fermi temperature is not practically possible. It is simply hypothetical. This means that free electrons cannot receive thermal energy equal to Fermi energy at ordinary temperatures. That's the meaning of this particular value. And in the next part, I tell you the definition of Fermi velocity. Fermi velocity is the velocity of electrons. Fermi velocity. Fermi velocity is the velocity of electrons which have occupied Fermi level. It can be expressed in terms of this equation. Vf is equal to 2EF divided by m power half. This is the rearranged form of EF is equal to half m v square. We know that half m v square is the kinetic energy. Here Fermi energy expression can be taken in terms of Vf. So on rearranging one can get this equation. So Fermi velocity is therefore defined as the velocity of electrons which have occupied the Fermi level. One more term that was introduced in the quantum free electron theory was effective mass. Effective mass. In the classical free electron theory, while defining the equation, that is expression for the electrical conductivity, it was defined as Ne square tau by m. By taking n as the number of free electrons per unit volume, E as the charge of electron, m was taken as the rest mass of electron, and tau is the relaxation time. So this was the equation derived by Drude and Lorentz in their classical free electron theory. In the quantum free electron theory, to overcome the limitations of classical free electron theory, Sommerfeld assumed that mass cannot be constant for the electron, especially in a metal having the periodic potential. There is the proof for describing the effective mass. Let us say h square k square divided by 8 pi square m. In my earlier lectures on the quantum mechanics, I was talking about the energy of a particle in a potential well of infinite height or depth, where we derived this expression. energy is equal to h square k square by 8 pi square and k is the wave number here. It's not Boltzmann constant. You can write it as 2 pi by lambda. So this equation suggests that the energy of a particle is depending directly on k and inversely on m, inversely on mass. Classical theory had assumed that the energy is independent of this mass. I mean, this was constant. Mass was considered to be constant. If that is the case, the energy should depend directly on k. But it was found that the energy was independent of k. It was verified experimentally, and in those experiments, it was observed that the energy was independent of k. But according to this equation, there should be some other parameter varying or changing this energy. The h value is constant. So it was assumed that energy depends on m, that is mass of electron. This equation was derived based on the Schrodinger's wave equation and wave function concept. And of course, de Broglie's concept of matter waves is also used. So it was concluded that the electron possesses a different mass in a crystal lattice that was named as effective mass. This arises from the combined effect of applied electric field and periodic electric potential due to ions. So the relation between the total energy of electron and the wave number k is here. This relation suggests that energy must depend on k if m is constant. But as I mentioned, if an electron moves within the periodic potential, energy does not vary with k. Hence m cannot be constant, and it varies in the region of periodic potential that results in effective mass. It is represented with the symbol m star. This is the effective mass, and quantum theory that corrects the classical theory by replacing m by m star, this correction is known as effective mass approximation. As an experimental evidence, effective mass was determined using cyclotron resonance experiments, and it was found to be different for different materials. It may be higher or smaller than actual mass m. Quantum theory corrected this value, and experimentally it was observed that for most of the transition metals, m star is greater than m. That is about 1.5 to twice the actual mass. But for semiconductors, it was found that m star is smaller than m. Effective mass was smaller than the actual mass of electron. Based on all such descriptions or the assumptions, quantum free electron theory finally arrived at the expression for electrical conductivity, that was n e square lambda divided by m star Vf. Here Vf is the Fermi velocity. One can observe that this tau, the relaxation time, is replaced by the ratio lambda by Vf, and m is replaced by m star. This is the modified expression for the electrical conductivity, or this is the expression for electrical conductivity of metals or conductors based on the quantum free electron theory. Now this is the time to understand the merits of the quantum free electron theory. We have understood the assumptions, and we have understood few definitions, which are the Fermi energy, effective mass, Fermi velocity, and Fermi temperature. Now let me tell you the merits of the quantum free electron theory or the success of the quantum free electron theory. The first and the foremost merit of the theory is about the specific heat of the conductor at a given temperature. In fact, classical free electron theory had assumed that every electron of the metal absorbs thermal energy. Hence, the specific heat at constant volume, that is Cv, must be high. But quantum free electron theory proposed that only a small number of electrons which are occupying the energy levels close to Fermi level. If this is the Fermi level, the electrons occupying the energy, that is occupying the energy levels closer to the Fermi level, can absorb the thermal energy. As a result, Cv is low. This is what was proposed by quantum free electron theory. And this theory arrives at the equation Cv is equal to 2K divided by EF into RT. R is the gas constant and T is the temperature at which the specific heat is measured, and EF represents the Fermi energy, K is the Boltzmann constant. By taking an approximate value of Fermi energy to be 5 electron volt, a typical value of Fermi energy for metals, it was shown that this part, that is 2K by EF, is equal to 10 power minus 4. That means Cv is 10 power minus 4 RT. This is what even experimentally showed, that a metal can have the specific heat at constant volume of the order of 10 power minus 4 RT. Means the specific heat at constant volume is very small for a given metal. Classical free electron theory had proposed that the specific heat at constant volume is high, and that theory did not even consider the dependence of specific heat on temperature. But quantum free electron theory corrected by saying that specific heat is very small and depends on temperature. It is very small because the electrons which are closer to the Fermi level are absorbing the thermal energy. Not all electrons, as described in classical free electron theory. That is the first merit. And the second merit was that temperature dependence of electrical conductivity. The second merit of the quantum free electron theory is about the temperature dependence of electrical conductivity. We have the equation. According to the quantum free electron theory, sigma is n square lambda by m star Vf. And this quantum theory has proved that this Fermi velocity is independent of temperature. So obviously the sigma lambda, that is the free path. This theory was able to show that lambda, that is mean free path, is inversely proportional to absolute temperature. Let us understand how this relation exists. When we increase the temperature of a metal, the thermal agitation will start taking place. That means the ions will vibrate about their mean position in all possible directions. If R is the amplitude of vibrations, the ions provide a circular cross section of area pi r square. There will be the circular cross section which blocks the matter waves, of moving electrons. The concept of matter waves was discussed in the previous lectures. We are talking about the quantum mechanics or the wave particle dualism. We have understood about the matter waves. So the waves that are associated with the electrons are blocked by such vibrations. That means electron waves are scattered by the cross section of this much area, that is pi r square. With increasing temperature, pi r square will also increase. That means r square will be directly proportional to temperature. This can decrease the mean free path of the electrons. That means lambda will be inversely proportional to absolute temperature. In this relation, we are observing that sigma is directly proportional to lambda. If lambda is inversely proportional to T, then sigma must be inversely proportional to absolute temperature. This is how quantum free electron theory corrected the second failure of classical free electron theory, in which the electrical conductivity was proposed to be inversely proportional to square root of absolute temperature. The quantum theory has shown that is not inversely proportional to square root of temperature, but it is simply the inversely proportional to temperature itself, sigma proportional to 1 by T. Another correction made by the quantum free electron theory was for the dependence of electrical conductivity on electron concentration, sigma and n relation. Classical free electron theory considered the relation between sigma and n alone. That did not consider the dependence of this electrical conductivity on the ratio of lambda by Vf and of course m star, that is the effective mass. So classical free electron theory limited itself to see the dependence of electrical conductivity on electron concentration. Quantum theory confirmed that the dependence is not only with the electron concentration, it also depends on the ratio lambda to Vf and the effective mass. Some metals having relatively small electron concentration n found to have high ratio, that is lambda by Vf, and small m star. This is high and this is small. For example, the value of this concentration in aluminium is 2.13 times greater than that of the copper. But lambda by Vf of copper is 3.73. For copper, this ratio lambda by Vf is 3.73 times 3.73 times greater than that of which metal? Aluminium. The value of m star is, that is effective mass, is 1.08 times that of copper. What does it indicate?